In a three-phase system, the factor 1.73, which is the square root of 3, is used to relate line-to-line and line-to-neutral voltages or currents. This factor arises from the phase difference between the three phases, which are typically 120 degrees apart. When dealing with three-phase power calculations, it is important to understand the relationship between line-to-line and line-to-neutral values, because some calculations require line-to-neutral values, while measurements are often taken line-to-line. Let's break down why this factor is essential. Consider a balanced three-phase system. In a balanced system, the magnitudes of the voltages and currents in each phase are equal, and the phase difference between each phase is 120 degrees. The line-to-line voltage is the voltage measured between any two of the three phases, while the line-to-neutral voltage is the voltage measured between one phase and the neutral point. The relationship between these voltages is key to understanding the 1.73 factor. The line-to-line voltage is 1.73 times the line-to-neutral voltage. This relationship can be derived using trigonometry and phasor diagrams, but the important takeaway is that the line-to-line voltage is always higher than the line-to-neutral voltage in a balanced three-phase system. The KVA, kilovolt amperes calculation formula often involves line-to-neutral values. However, equipment specifications and measurements are frequently given in line-to-line values. To use the formula correctly, you might need to convert from line-to-line to line-to-neutral. The formula for calculating KVA in a three-phase system is KVA equals volts times amps times 1.73 divided by 1000, where volts and amps are the line-to-neutral voltage and current, respectively. If you are given line-to-line voltage and current, you must first convert them to line-to-neutral values before applying the formula. To convert line-to-line voltage to line-to-neutral voltage, you divide the line-to-line voltage by 1.73. Similarly, to convert line-to-line current to line-to-neutral current in a balanced system, you divide the line-to-line current by 1.73. Now, let's address the assumptions that are typically made when performing these calculations. Firstly, it is assumed that the system is balanced. A balanced system means that the voltage and current in each phase are equal in magnitude and are 120 degrees apart. If the system is not balanced, the calculations become more complex, and you cannot simply use the 1.73 factor for conversion. Secondly, it is often assumed that the power factor is 1.0. The power factor is the ratio of real power, kilowatts, to apparent power, KVA. A power factor of 1.0 means that the voltage and current are in phase, and all the apparent power is being used as real power. If the power factor is not 1.0, you need to take it into account when calculating the real power, kilowatts. The formula becomes kilowatts equals KVA times the power factor. To illustrate this, consider an example where you have a three-phase system with a line-to-line voltage of 208 volts and a line-to-line current of 21 amps. To calculate the KVA, you first need to convert these values to line-to-neutral. The line-to-neutral voltage is 208 volts divided by 1.73, which is approximately 120 volts. The line-to-neutral current is 21 amps divided by 1.73, which is approximately 12.1 amps. Now, you can use the KVA formula. KVA equals 120 volts times 12.1 amps times 1.73 divided by 1000, which gives you approximately 2.51 kVA. This is the apparent power of the system. If the power factor is 1.0, then the real power is also 2.51 kilowatts. However, if the power factor is, say, 0.8, then the real power is 2.51 kVA times 0.8, which is approximately 2.1 kilowatts. Let's delve deeper into the concept of balanced versus unbalanced systems. In a perfectly balanced system, the loads on each phase are identical, resulting in equal current flow in each phase and equal voltage drops. However, in reality, perfectly balanced systems are rare. Imbalances can arise due to uneven distribution of single-phase loads, equipment malfunctions, or variations in line impedances. When a system is unbalanced, the 1.73 factor cannot be directly applied to convert between line-to-line and line-to-neutral values. Instead, more complex calculations involving symmetrical components or phase-by-phase analysis are required to accurately determine the voltages and currents in the system. Symmetrical components involve decomposing the unbalanced three-phase system into three balanced systems: a positive sequence, a negative sequence, and a zero sequence. These sequence components can then be analyzed separately, and the results can be combined to determine the actual voltages and currents in the unbalanced system. Phase-by-phase analysis involves analyzing each phase separately, taking into account the individual loads and impedances in each phase. This method is more computationally intensive but can provide accurate results even in highly unbalanced systems. Now, let's discuss the power factor in more detail. The power factor is a measure of how effectively electrical power is being used. It is defined as the cosine of the angle between the voltage and current waveforms. A power factor of 1.0 indicates that the voltage and current are perfectly in phase, and all the apparent power is being used as real power. A power factor less than 1.0 indicates that the voltage and current are out of phase, and some of the apparent power is being wasted as reactive power. Reactive power is power that is stored and released by inductive and capacitive elements in the circuit. Inductive loads, such as motors and transformers, consume reactive power, while capacitive loads, such as capacitors, supply reactive power. When the power factor is low, the current flowing through the circuit is higher than necessary to deliver the required real power. This increased current leads to higher losses in the conductors and equipment, as well as reduced voltage levels. Therefore, it is desirable to maintain a high power factor to improve the efficiency and performance of the electrical system. Power factor correction can be achieved by adding capacitors to the circuit to compensate for the reactive power consumed by inductive loads. The capacitors supply reactive power, which reduces the amount of reactive power that must be supplied by the source, thereby improving the power factor. In summary, the 1.73 factor is a crucial component in three-phase KVA calculations, allowing for the conversion between line-to-line and line-to-neutral values. However, it is important to remember the assumptions that underlie these calculations, namely that the system is balanced and the power factor is 1.0. If these assumptions are not valid, more complex methods may be required to accurately determine the KVA and real power in the system. Understanding these concepts is essential for anyone working with three-phase electrical systems. It is good to understand the relationship between KVA, kilowatts, and power factor. KVA, kilovolt amperes, is the apparent power, which is the product of voltage and current. Kilowatts is the real power, which is the power actually consumed by the load. The power factor is the ratio of kilowatts to KVA, and it represents the efficiency with which electrical power is used. A high power factor is desirable because it minimizes losses and improves the overall efficiency of the electrical system. Reactive power, measured in volt-amperes reactive force, is the power that is stored and released by inductive and capacitive elements in the circuit. Inductive loads, such as motors and transformers, consume reactive power, while capacitive loads, such as capacitors, supply reactive power. Reactive power does not contribute to the real work done by the load, but it does contribute to the overall current flow in the circuit. Power factor correction involves adding capacitors to the circuit to compensate for the reactive power consumed by inductive loads. The capacitors supply reactive power, which reduces the amount of reactive power that must be supplied by the source, thereby improving the power factor. In addition to improving efficiency, power factor correction can also reduce voltage drop and increase the capacity of the electrical system. Voltage drop is the decrease in voltage along a conductor due to the impedance of the conductor. A low power factor can increase voltage drop, which can lead to equipment malfunction and reduce performance. Power factor correction reduces the current flow in the circuit, which in turn reduces voltage drop. The capacity of an electrical system is the maximum amount of power that it can deliver without exceeding its design limits. A low power factor can reduce the capacity of the electrical system, because the increased current flow takes up more of the system's capacity. Power factor correction reduces the current flow, which frees up capacity and allows the system to deliver more power. In summary, the 1.73 factor is a key component in three-phase power calculations, but it is important to understand the assumptions and limitations associated with its use. A balanced system and a power factor of 1.0 are ideal conditions, but in reality, systems are often unbalanced and power factors are less than 1.0. In these cases, more complex methods may be required to accurately determine the power in the system. Understanding these concepts is essential for anyone working with three-phase electrical systems. Furthermore, let's consider the impact of harmonics on KVA calculations. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency, typically 50 Hz or 60 Hz. Nonlinear loads, such as electronic devices, can generate harmonics, which can distort the voltage and current waveforms. These distorted waveforms can affect the accuracy of KVA calculations. When harmonics are present, the KVA is no longer simply the product of the root mean square, RMS, voltage and current. Instead, the KVA must be calculated by taking into account the harmonic content of the waveforms. This involves calculating the total harmonic distortion, THD, of the voltage and current waveforms, and then using these values to adjust the KVA calculation. The total harmonic distortion is a measure of the amount of harmonic content in a waveform. It is defined as the ratio of the RMS value of the harmonic components to the RMS value of the fundamental component. A high THD indicates that the waveform is significantly distorted, while a low THD indicates that the waveform is relatively sinusoidal. When harmonics are present, the KVA is given by the formula KVA equals volts times amps times the distortion factor, where the distortion factor is a function of the THD of the voltage and current waveforms. The distortion factor is always less than or equal to 1.0, and it represents the reduction in KVA due to the presence of harmonics. Harmonics could also cause other problems in electrical systems, such as overheating of equipment, increased losses, and interference with communication systems. Therefore, it is important to mitigate harmonics whenever possible. Harmonic mitigation techniques include using harmonic filters, which are designed to block or reduce the flow of harmonic currents, and using harmonic reducing transformers, which are designed to minimize the generation of harmonics. In conclusion, KVA calculations in three-phase systems can be complex, especially when dealing with unbalanced systems, non-unity power factors, and harmonics. Understanding these concepts is essential for ensuring the accurate and efficient operation of electrical systems. Careful consideration of these factors will contribute to reliable and optimized electrical system performance. Remember that the factor 1.73 is derived from the geometry of the three-phase system, specifically the 120-degree phase displacement between the three phases. This displacement creates a specific relationship between line-to-line and line-to-neutral voltages and currents. When the system is balanced, meaning that the loads are evenly distributed across the three phases, this relationship simplifies to the line-to-line voltage being equal to the square root of 3, approximately 1.73 times the line-to-neutral voltage. If the system is unbalanced, this simple relationship no longer holds, and the calculations become significantly more complex. You would need to apply more advanced techniques such as symmetrical components to properly analyze the system. In addition to the balance condition, another key assumption when using the 1.73 factor is that the voltage waveforms are sinusoidal. If the waveforms are non-sinusoidal, which can occur due to the presence of harmonics, the relationship between line-to-line and line-to-neutral voltages becomes more complicated. Harmonics are caused by nonlinear loads such as electronic devices, variable frequency drives, and some types of lighting. These loads draw current in a non-sinusoidal manner, injecting harmonic currents back into the electrical system. These harmonic currents can distort the voltage waveforms, making the 1.73 factor inaccurate. In such cases, more sophisticated power quality analysis techniques are needed to accurately determine the voltages, currents, and power in the system. So, while the 1.73 factor is a useful tool for quick calculations in balanced, sinusoidal systems, it's essential to be aware of its limitations and to use more advanced methods when dealing with imbalanced or non-sinusoidal conditions. These advanced methods may involve using specialized software or equipment to analyze the system and determine the true voltages, currents, and power. Remember, electrical systems can be complex, and it's always best to consult with a qualified electrical engineer when dealing with situations outside the scope of simple calculations. This ensures safety and accuracy in your electrical system design and analysis. Lastly, always remember to consult local electrical codes and standards, such as the National Electrical Code (NEC) or the Canadian Electrical Code (SEC), for specific requirements related to KVA calculations and electrical system design. These codes provide detailed guidelines for safe and compliant electrical installations. They often include specific tables and calculation methods for determining conductor sizes, overcurrent protection, and other aspects of electrical system design. Failure to comply with these codes can result in safety hazards and legal issues. Therefore, it's essential to be familiar with the applicable codes and standards in your area and to follow them carefully. In addition to the NEC or CEC, there may be other relevant standards, such as those published by the Institute of Electrical and Electronics Engineers, IEE, or the International Electrotechnical Commission, IEC. These standards provide guidance on specific aspects of electrical system design and operation, such as power quality, grounding, and protection. Staying up to date with the latest versions of these codes and standards is crucial for ensuring the safety and reliability of your electrical systems. Furthermore, when performing KVA calculations, always consider the diversity factor and demand factor. The diversity factor is the ratio of the sum of the individual maximum demands of a group of loads to the maximum demand of the entire group. The demand factor is the ratio of the maximum demand of a load to its total connected load. These factors are used to account for the fact that not all loads will operate at their maximum demand simultaneously. Using these factors can help to avoid oversizing electrical equipment and reduce costs. Finally, it's always a good practice to document your KVA calculations and assumptions. This documentation can be helpful for future reference and for troubleshooting any problems that may arise. Be sure to include all relevant information, such as the voltage, current, power factor, and any applicable diversity or demand factors. This documentation should be kept in a safe and accessible location.